Welcome to the second part of the BoxBot tutorial. From last part, we built a ragdoll model from the BoxBot. Let's do a quick sanity check, make sure everything is fine. The feet looks a bit too light. Let's make the feet heavier. So now the joints looks fine. Just double check if we drop it, it should ragdoll as expected. Cool. So next step is to put controllers on it. First, put an empty one. And we need to add a TNT humanoid controller to the controller object. It's like that. In general, the humanoid controller is fairly complicated to configure. We recommend you go to our web pipeline here, use a SimRig editor to configure that, and use the output as a template for you to further tune it. However, in this tutorial, we focus on UGC developers, so we bypass that, and we'll try to do the hard things from the editor. So, you need to specify the control parameters, which is script object, and you can create from scratch. But in this case, we'll find some existing control parameters called the humanoid CP 3-point tracking that's included in the avatar alpha package under the DeepMotion/runtime/demo scripts folder. So you just drag that to the slot. We do need to make an edit to this since this script is not tailored for this biped apparently. As you can see, there are about 100 parameters here. We need to tune it so it works. Okay, so before we do anything, we need to go back to the biped, to the TNT humanoid controller, make sure we configure the essential limbs under the limbs configuration. So the most important thing is the feet. Let's drag the L feet to the L toes, and drag the R foot to the R toes. By the way, we can have multiple joints on the feet. You can have toe joints, ankle joint. But in this case, we build a simplified model, so we just have feet. We just assign feet to the toes. That's okay. I think that's it. I mean, we just assign the 2 feet. We don't really have other upper torso parts yet. So with these 2 assigned, let's see how it looks like. Press play and run simulation. So, well, it looks like the biped is standing there. You can double click the control parameter in runtime, so that brings you to the editor, the inspector, to the control parameters. You can tune this runtime. One thing that gyro I want to point out. So gyro is a helper force applied to the torque, applied to the root to assist the balance. When you reduce gyro to 0, that will be entirely physics-based balancing. So it's good to see its balance looks pretty good, but we do want to see whether without any external force help this can balance okay. So let's stop the simulation and let's edit that control parameters. Let's make a copy of that first so we don't corrupt the original one. Let's just call it a box control. Assign box control to the control parameters. Okay, let's go down all the way to this gyro. Let's make it 0. 0 gyro means purely based on physics, no external force helper. And in this case, we can test the balancing capabilities better. Let's drop it again to see whether it fall down. Still okay. Okay, and let's play with it a little bit. Set the pelvis to be kinematic so that you can drag it around during runtime for our testing. So now we can drop this. Okay, so it looks like the legs have no strength at all. It's floppy. The reason of that is we need to configure the muscle strength on the leg. In the technical term, there are kpkd parameters under the control pose tracking setting. So for L heap, R heap, we'll give it something like maybe 250 and 25 for the knees. So Kp is basically the strength of the muscle at that joint, and Kd is like the stiffness or the friction at that joint. And kpkd are actually the standard PD controller terms you used in robotic control quite a bit. So by giving a non-zero kpkd, you actually assign some strength to the joints. Only with that strength we can control the pose of the character. So here, let's actually finish the assignment. For knees, you don't need that strong knees. Maybe just 50, maybe enough. This need for foot, you actually need quite a bit strength on the feet. So let's give it maybe 125. Okay, now let's drop it again to see how it looks like. Okay, it's still kinematic, the root, so we can actually move it around. So it looks like it might be okay. So let's uncheck the kinematic to drop it on the ground. Okay, it fly away. So we still have work to do. The first thing we need to adjust is the desired height for this guy. So as you can see, the pelvis is at a height of 1.0, right? And when it drops to the ground, the height will be lower than 1.0. So we need to make sure our control parameters to match that. So desired height here, maybe 1.1 is too high. Maybe let's just give it something like 0.9. And the standing still threshold means if you have velocity bigger than that, it's trying to walk. 0.4 is probably too high. Give it lower. And yeah, let's see how this works. Drop it. Oh, we forgot to uncheck the kinematic flag. Uncheck it so it won't be anchored in the ground. Sorry, in the air. So it's not too bad, except that the feet looks too frailing, and maybe you can make the feet heavier. And the desired height does looks like too low. Make it 1 so it stands up a little bit. And what else? Maybe the torso is too heavy. Let's reduce it to 75. Do another quick check. Okay, so it looks about fine. The next, we want to make this guy walk around. For that, you need to attach a driver script to the guy. So let's add a script component. Let's call it a humanoid driver. It's a new script. Create and add. Okay. And then let's edit this script. Okay, so we don't need this default script. Humanoid driver. Yeah, this is default script. We don't need it. So I'll copy paste in the script I already created. Let's rename that to humanoid driver to match the file name. Okay. What this script does, it basically it performs local motion control. It invokes the API of the underlying humanoid controller to set the velocity and to set the heading. So these are the two most important locomotion APIs you can invoke from the script to steer around that robot. The script is pretty simple. It basically takes keyboard input, from the horizontal and vertical axis, and these are like a WASD control. And you take the input, you map them to velocities, and you also map them to desired heading, and then just call the API every frame to steer the robot or to accelerate the robot or to brake the robot. Yeah, I won't go into detail of the script, but you can read a little bit about it yourself. Okay, so let's see how it works. Now we attach the humanoid driver script to it. It allows us to use WASD keyboard to drive the robot. But of course, I don't expect it to work. We need to tune the controllers quite a bit. So it's standing still. If I press W now, it doesn't respond to me. Oh, okay, now it responds. So it looks like not very stable. Let's make the torso lighter, 50. Also for the debugging purpose, let's turn on the gyro so we can debug it more easily. Now let's give it a 0.5 gyro there to help us debug. Wow, it falls. Oh, so we need to make sure the humanoid is simulated at a high enough frequency. Double check the world. We are running at 60 Hz, which is good. But in general, for the biped, we need biped to be stepped at a little bit higher frequency. So there's a nice feature under TNT base. It's called simulation frequency multiplier. So basically, you can remain the entire world to be simulated at 60 Hz, which is good for your performance. And you can only you can just say for this robot, bump up the simulation frequency with a multiplier here. Let's give it 8. So that will make the robot to be simulated at 480 Hz, which will give much better control. And let's see how that works. Looks much nicer, huh? And now let's use keyboard try to walk around. Okay. So the walking are not perfect yet, but let's tune the physics control parameter more. If we check out these 100 parameters, a lot of them are actually trajectories to fine-tune the leg motion. Among them, you can find out we have a bunch of trajectories for the toes. Since this robot doesn't have a toe, so we don't want to add this trajectory. It makes, we see some weird feet dancing, it because we have this use this toe trajectory, we should just flatten it. Hopefully the feet will keep parallel to the ground. So let's just zero the toe trajectory in the control parameters. What it does is trying to then keep the feet flat. Let's see how that go. Okay. So I think it moves better, but it glides around. Oh, one thing is it might be the friction is too low. So let's assign some physics material to the feet to make it more friction. Go to the feet and go to the TNT link. Go to the material and select rubber. Let's select the ground and assign the rubber material to the ground as well. And let's save just in case. So now let's play it again and see how the friction feels. I think it's better, although the step width is too wide. We can also adjust that. So let's go to let's run it again. You can adjust the control parameter in the runtime this way, but the result will not be saved to disk. But it's good for quick experiment. Once we find the good numbers, we can then permanently change the script object on file to make it static. So for now, if you look at the parameter set, you can see there's a step width. We probably need to reduce it a little bit. Let's see how that works. I think desired height might be too low. Let's make it taller. Desired height maybe, let's say 0. Maybe it's, you see, we can control desired height here. Okay, let's just make it to be 1 point, maybe 0.95. So check our overall build to see if they are balanced. A lot of this is like building real robots. You have to make sure the physics thing is balanced. The pelvis, 50. We don't have a torso, but generally we need a heavy torso to stabilize it. So for the hip, 5 maybe need to be bigger. Maybe this one need to be bigger, and the KBKD, the strength on the hip, probably need to be stronger. Let's try at 500 instead. So while it's walking, let's adjust the step width. Hopefully it doesn't do that. Hopefully it doesn't do the swaying too much. So continue and the step width. Okay. So we just measure the step width at about 0 and make it at 0. Another thing is to make it simpler. for now, we can let's look at the base TNT base, actually the biped controller game object, to make sure the global parameters are okay. To make it simpler, right now we can disable the self collision so that the legs will not scratch with each other. Disable that. Also, let's double check the controller top level config. One thing we haven't configured right is here. There's this step relative to COM or root thing. Yeah, in general, we want the swing model of the leg to be relative to the root, right? Especially for this biped case, because you don't have upper torso, then the center of mass would be too low. It's generally safe to do the stepping. Let the stepping to be pivot around the root. So we forgot to check that before. So we check this here, and yeah, let's see how that works. So it can walk. It can do some turning. It can do backward. Although there are a little bit leg crossing for the backward. Okay, I think we made the progress, right? Overall, the biped is, it can walk, but still we might want to adjust the balance a little bit. I think this torso probably is, in general, for the worker, you maybe want to be a little bit front. Make it a little bit more balanced towards the forward. For the hip, maybe the hip is too outside, so we can adjust it a little bit. Like just make the hip a little bit inward. And see how it goes. Yeah, let's make the feet a little bit forward, like a real human. adjust the pivot. Check to see if they match. So let's make the leg lighter. I think the step width is too narrow now after this adjustment. So let's put it back to some value, maybe 0.2. Wow, interesting. 0.05. I think it's a bad idea to make the two hip joint so innerward. So let's move it back. That. And now reduce the step width. It's 0. Now it works pretty nicely. Although the leg crossing seems to be more severe, we can probably just make the step width a little bit bigger, 0.05. Okay, yeah, we're in the fine-tune space to make it look visually and physically, compromise. I think this looks fine. Just keep in mind that a pure biped without upper torso this one actually pretty challenging to balance. Think about it in real life. If you don't have your upper torso or arms, it will be hard to balance. But I think what we achieve here is pretty nice, given that it's just 20 minutes quick build from scratch. Our robot now can walk forward. It can, I can stop and it can standing still. It can also move backward. And if you press Q and E in the script, the robot will move sideways. We actually can control the speed. So now I'm stepping a little bit harder. I'm stepping a little bit further. It's less stable when it's trying harder to to step. Okay, finally falling down because we assigned 0 external force to help it. So what you see is actually entire self-balanced robot just based on internal torques. That's what we can achieve in the past half an hour. Thank you for part 2 of the tutorial. In the next part, we'll talk about how to build the upper torso for this biped.